Question 1. If an electron is traveling due east with a speed of 3 kilometers per second through the Earth's magnetic field, which has a magnetic field strength of 50 microtesla, how much magnetic force is that electron experiencing? Please pause the video and try this problem on your own. To solve this problem, let's first look at the information we have. First off, we know it's an electron. That gives us a particular charge. It also gives us a particular mass if we need it. We know that the direction is due east. We know that the speed is 3 kilometers per second, which in MKS units is 3 times 10 to the third meters per second. We know the Earth's magnetic field has a magnetic field strength of 50 microtesla, which is equivalent to 5 times 10 to the negative fifth Tesla. We also know that since it's the Earth's magnetic field starts at the South Pole and goes up to the North Pole. Since the question asks how much magnetic force, that means we are looking for the magnitude. And so we can use F is equal to Q V cross B using the AB sine theta form of the cross product. This means we can use the formula F is equal to QVB sine theta. So the values we know, Q, that's the charge on an electron, is negative 1.6 times 10 to the negative 19th coulombs. V was 3 times 10 to the third meters per second. And B is 5 times 10 to the negative fifth Tesla. Now the negative sign on the charge does not matter for this question because, again, we are looking for magnitude, and the negative sign will affect the direction. In order to find theta, we need to think about the geometry of the problem. The electron is traveling due east, and the Earth's magnetic field goes from south to north. So the direction of the Earth's magnetic field is north, the direction of the electron's travel is east. These two directions are perpendicular, so the angle between them is 90 degrees. Plugging these values into our formula, F is equal to QVB sine theta, force is equal to 1.6 times 10 to the negative 19th coulombs, times 3 times 10 to the negative third meters per second, times 5 times 10 to the negative fifth Tesla, times the sine of 90 degrees, or 2.4 times 10 to the negative 20th newtons. Question 2. What direction is the force on the electron? Please take a moment to try to solve this problem yourself. With the given information, our best bet is to use the right-hand rule to solve this. So the information we know, the electron is traveling due east through the Earth's magnetic field, which again is going towards the north. So if we take our right hand and hold it so that our thumb is pointing in the direction of the electron towards the east, and our fingers are pointing in the direction of the magnetic field towards the north, then our palm is pointing in the direction of force. In this example, our palm is pushing away from the surface of the Earth, or up. However, since the electron is negatively charged, the direction is the opposite of this. The direction of force that this electron experiences is down, or into the Earth. Question 3. A particle has a charge of 0.3 millicoulombs. It is traveling with a velocity of v is equal to 20 meters per second I hat plus 15 meters per second j hat through a magnetic field given by B is equal to 10 Tesla I hat minus 10 Tesla j hat. What is the force acting on this particle? Please pause the video and attempt this problem yourself. To solve this problem, we are going to have to use the vector form of the cross product. Now, if you'll recall during my lecture, I used a number of different methods of finding the cross product, so I am going to solve this problem two different ways. For the first way, I am going to use the vector identities. I hat cross j hat is equal to k hat, j hat cross I hat is equal to negative k hat, I hat cross I hat is equal to 0, etc. So we use the formula F is equal to Q times V cross B. Q is a scalar, so Q will have a value of 3 times 10 to the negative 4th coulombs, and it will not affect the cross product. Our two vectors that we are cross producting, V is 20 meters per second I hat plus 15 meters per second J hat, and B is 10 Tesla I hat minus 10 Tesla J hat. So in order to be able to use these vector identities, we are going to use the FOIL method to multiply the velocity and the magnetic field. Recall FOIL stands for first, outer, inner, last. So first, we multiply the first term of velocity and the first term of magnetic field. 20 meters per second I hat cross 10 Tesla I hat. Outer, we multiply the first term of the velocity by the second term of the magnetic field. And remembering that this minus sign means that that term is negative 10 Tesla, which gives us 20 meters per second I hat cross negative 10 Tesla J hat. Third is inner. We look at the second term of V and the first term of B. 15 meters per second J hat cross 10 Tesla I hat. And last, we look at the second term of V and the second term of B to give us 15 meters per second J hat cross negative 10 Tesla J hat. Now the first terms and the last terms are easy. The first term has an I hat cross I hat. The last term has J hat cross J hat. I hat cross I hat and J hat cross J hat are both 0. So both of those terms go to 0. The outer and inner terms. The outer term is I hat cross J hat. So we go here, I hat cross J hat is equal to K hat. So we have 20 meters per second I hat cross negative 10 Tesla J hat. 20 meters per second times negative 10 Tesla is negative 200 Tesla meters per second. I hat cross J hat is K hat, and so we have negative 200 Tesla meters per second K hat. For the inner terms, we have 15 meters per second J hat times 10 Tesla I hat. J hat cross I hat is negative K hat. 15 meters per second times 10 Tesla is 150 Tesla meters per second. So that's 150 Tesla meters per second in the negative K hat direction. Now we combine the terms 0 minus 200 Tesla meters per second K hat minus 150 Tesla meters per second K hat plus 0. And we get negative 350 Tesla meters per second K hat. There is no I or J components. This is reasonable because both V and B are purely in the IJ plane. Since their cross product needs to be perpendicular to both of these vectors, the only vector that is perpendicular to two vectors in the IJ plane is a vector either in the positive K hat or the negative K hat direction. So 3 times 10 to the negative 4th coulombs times negative 350 Tesla meters per second K hat, we end up with negative 0.105 newtons K hat. Second method we could use is by using this formula right here, where the I component is BJCK minus BKCJ, etc. So again, that charge is a scalar which we're going to plug in here and then deal with later. we're going to look at the cross product of v and b. So the cross product of v and b, v is our first term, which is, confusingly enough, the b of this formula, and b is a second term, which makes it the c of this formula. So the I component of A should be the j component of V times the k component of B minus the k component of V times the j component of B. The j term should be the k component of V times the I component of B minus the I component of V times the k component of B. And the k term should be the I component of V times the j component of B minus the j component of V times the I component of B. Since both velocity and magnetic field have zeros for their k component, we get a lot of zeros in our I and j terms, enough that there is no I and j component. So all that we're left with is the k component. 20 meters per second times negative 10 Tesla minus 15 meters per second times 10 Tesla. And we are back to where we were at the end the first time we solved this problem. And so we get the same answer.